Mars does not punish us because it is far away. It punishes us because we are still trying to cross an ocean with a matchstick. Every mission to Mars begins with a countdown that looks powerful. Fire pressure steel, a tower, shaking under its own violence. But after the rocket has done its work, the spacecraft becomes almost helpless. It coasts. For months, it falls through sunlight. Not fast enough to arrive when we want. Not heavy enough to carry what we need. Not free enough to leave when the planets are inconvenient. That is the quiet limitation behind the dream of Mars. It is not courage. It is not imagination. It is fuel. Right now, Earth and Mars only give us a useful launch window about once every 2 years. Miss it, and the solar system closes the door. Hit it, and you still have to send everything across millions of kilometers with almost no room for waste. A rover the size of a car becomes a triumph. A human landing system becomes a nightmare of mass. A permanent presence becomes something much harder than planting a flag. So NASA is now chasing a different idea. Not a bigger explosion. Not another version of the same chemical rocket. A spacecraft that carries a nuclear reactor, makes its own electricity, and pushes through deep space like a freight train crossing a continent, slowly at first, then relentlessly. The promise sounds almost absurd. A nuclear railroad to Mars. A way to move cargo power instruments and eventually human infrastructure through the solar system with a kind of efficiency rockets were never built to provide. But the real question is not whether nuclear propulsion can work. The real question is what it costs to turn space from a place we visit into a place we can supply. The popular version of Mars exploration is simple. Build a larger rocket. Put more fuel under it. Push harder. That story is comforting because it makes the problem look like scale. As if Mars is only waiting for a machine big enough to bully physics into cooperation. But rockets are not just vehicles. They are bargains. Every kilogram you send toward Mars must be paid for with more propellant, more structure, more engines, more launches, and more risk. The spacecraft becomes a pyramid of sacrifice where most of the machine exists only to move the rest of the machine. This is why chemical rockets are so violent and so wasteful at the same time. They produce enormous thrust for a few minutes, then spend the rest of the mission obeying the trajectory they purchased in that brief fire. For robotic exploration, this has worked beautifully, carefully, slowly. But the moment you stop sending instruments and start sending infrastructure, the math changes. Habitats are heavy. Power systems are heavy. Radiation shielding is heavy. Return fuel is heavy. Spare parts are heavy because Mars does not have a warehouse. The dream of settlement collapses into logistics. This is what NASA is trying to change with Space Reactor-1 Freedom. The agency says the spacecraft is planned to launch to Mars before the end of 2028, using nuclear electric propulsion and carrying the Skyfall payload of Ingenuity-class helicopters. That does not mean a nuclear rocket blasting away like a bomb. It means a reactor making electricity. Electricity feeding thrusters. Thrusters pushing gently for a very long time. The force is small. The implication is not. Because a spacecraft that can keep pushing does not behave like a cannon shell. It behaves like a transport system. And the first wall is hidden inside that word system. The first major wall is thrust. Nuclear electric propulsion does not feel like a rocket. It does not roar. It does not tear itself away from Earth. It cannot lift a spacecraft off a launch pad or push through an atmosphere or win a fight against gravity in the first few minutes. It only becomes powerful after the violence is over. That is the part people miss. Space Reactor 1 still needs a conventional rocket to get into space. The nuclear system begins its real work only once the spacecraft is already in orbit, where there is no air, no runway, no friction, and almost nothing to push against except time. An ion thruster is efficient because it wastes very little. But efficiency is not the same as force. It can throw charged particles out of the back of a spacecraft at extreme speed, yet the total push can still be gentle enough that on Earth it would feel almost meaningless. In deep space, meaningless things accumulate. A tiny force applied for weeks becomes a different kind of engine. Then for months. Then across millions of kilometers. The spacecraft is not punched toward Mars. It is persuaded. This is why the reactor matters. Solar panels become less useful the farther you travel from the sun. Chemical fuel disappears the moment you burn it. But a fission reactor carries a dense source of energy inside the spacecraft itself, turning heat into electricity and electricity into motion. NASA describes SR-1 Freedom as a nuclear electric propulsion demonstration meant to build flight heritage and set precedent for future fission systems in deep space. And this changes the meaning of speed, not launch speed, not the violent speed we understand from rockets. Operational speed, the ability to leave more often, carry useful cargo, keep power alive when sunlight is weak, build a route that does not depend entirely on one perfect burn and one narrow planetary alignment. But once you put a reactor on a spacecraft, propulsion is no longer the only problem. Now the hidden system wakes up. The deeper problem is not making electricity. It is surviving everything electricity creates. A reactor in space is not a generator bolted to a spacecraft. It is heat radiation, mass shielding policy, failure analysis, launch approval, and decades of institutional fear compressed into one machine. On Earth, a power plant can dump waste heat into water, air cooling towers, and enormous structures that never have to move. In space, heat has nowhere convenient to go. There is no wind, no ocean, no ground. Only black vacuum where every unwanted watt has to be radiated away through panels that must be light enough to launch and strong enough to survive deep space. This is why the spacecraft cannot just be compact. It has to be stretched. The reactor must sit far from the electronics. A shield must protect the vehicle without making the system too heavy to be useful. The power conversion unit must turn reactor heat into electricity for years because no one is flying out to fix a turbine between Earth and Mars. And before any of that matters, the spacecraft has to leave Earth safely. That is the hidden burden of nuclear spaceflight. The reactor cannot simply be treated like another engine. It has to earn permission to exist on top of a rocket under launch vibrations above an inhabited planet, with every failure mode studied before the countdown ever begins. NASA's own framing of SR-1 Freedom is not just about reaching Mars. It is about creating flight heritage, regulatory precedent, and an industrial base for future fission systems. The spacecraft is a technical mission, but also a legal and political first step. That is what makes this more than propulsion. If it works, Mars gets closer. But the larger achievement is stranger. Humanity learns how to carry a small, controlled star through the dark without destroying the machine around it. The consequence is not that Mars suddenly becomes easy. It becomes logistical. That is a colder and more important word. Exploration is something you do once. Logistics is something you survive by repeating. A base on another world is not built by hero missions. It is built by cargo arriving before anyone needs it. Power units, spare parts, communication relays, surface vehicles, drilling systems, return propellant equipment, machines that have to be there before human beings can safely follow. This is where nuclear electric propulsion becomes more than an engine. NASA describes SR-1 Freedom as a way to demonstrate efficient mass transport in deep space, while also building the precedent for future fission systems across propulsion, surface power, and long-duration missions. That phrase sounds bureaucratic, but underneath it is a different future. A future where the moon is not just a destination, but a proving ground. Where Mars is not just a horizon, but a supply chain. Where the outer solar system stops being a place for one fragile probe every decade and becomes a territory where high-power spacecraft can actually work. Because sunlight fades. Beyond Mars, solar panels must grow larger and weaker at the same time. Past Jupiter, the sun is no longer the generous star we know from Earth. It becomes a distant lamp. Nuclear power changes that relationship. It lets a spacecraft carry its own fire into places where the solar system goes dark. But every new capability creates a new dependency. Once you can move more cargo, you start designing missions that require it. Once you can supply a world, you start depending on the supply line. The railroad does not just open the frontier. It makes the frontier vulnerable to schedules, failures, budgets, politics, and machines that must keep working in silence. Mars will not be conquered by bravery. It will be negotiated with infrastructure. And the first negotiation begins with one reactor, one spacecraft, and a long, quiet burn toward a planet that has never made room for us. A nuclear railroad to Mars is not the fantasy version of the future. It is not silver cities under glass domes, or ships moving casually between worlds, or humanity suddenly becoming immune to distance. It is something quieter. A machine leaving Earth with a reactor inside it. A faint electric push. A year of cold travel. A payload released into the thin Martian sky searching for flat ground and buried ice before any human footprint is allowed to follow. That is what progress looks like when the universe refuses to care about us. Not a leap, a system. The solar system is not empty in the way a room is empty. It is empty in the way an ocean is empty. Vast, hostile, indifferent, and expensive to cross. Every new route must be paid for with energy. Every kilogram must justify itself. Every failure becomes part of the distance. Chemical rockets gave us access to space, but they did not make space manageable. Nuclear power may be the first tool that begins to change that. Not by making exploration safe, not by making Mars close, but by giving spacecraft the one thing deep space always takes away from them: endurance. And that is the real threshold. If Space Reactor-1 works, it will not mean humans have mastered Mars. It will mean we have built the first piece of a supply chain into a place that still does not want us there. A railroad does not tame a frontier. It only proves we are willing to return.